Now we invite Professor Amir Khorrami Chokami, okay, from the University of Torino.
So, thank you for inviting me today to this meeting. I will talk extremal dependence between maximum of concomitance, and let me cite Marie Kratz, full professor at ESSEC University in Paris and director of the CREAR. Before we get started with the motivations and the results of our work, let me just define what is a concomitant. So basically, here you have a sequence of bivariate random vectors, and we need them to be continuous because we want to avoid ties. And basically what we do is reorder the sequence by means of the first entry. So here you have the minimum, here you have the maximum. And then how do we define the concomitant? Well, for example, if x2 is the minimum, then y2 will be the concomitant of the minimum. Okay, so we look at the variable associated in the original to the higher order statistic in the original sequence. Concerning the motivations, I also prepared a background on extreme values in general. It's obvious why extremes are of interest nowadays. For example, in the northern part of Italy, we come from 18 months of drought, which created huge problems of air pollution and ended in thunderstorms, which created floods as well recently in the Emilia-Romagna region. So this concerns the study of environmental extremes, but we can also look for fires or cyber attacks, so in the context of insurance risk, or if you want to think to, let's say, positive examples, athletics are concerned with record theory. So the happening of a record in a sequence of random variables, where record is a max or a min. The main problem in studying extremes not only concerns univariate sequences, but multivariate sequences, because the interest in studying the dependence that we can have among extreme values, where an extreme can be a max or a observation which exceeds a high threshold. And studying dependence at extreme levels is a very difficult task. We believe with Marie Kratz that concomitance can give us a new point of view in tackling this problem. So just a quick recap of extreme values. Take an IAD sequence of random variables, and the problem is study the max, and we know that this is the exact distribution of the max in the IAD case. But what if f is unknown, which happens in general? We cannot use the empirical CDF, because you can say, okay, just use the empirical and plug the empirical there and you have the estimate. Is not so simple, because we want to extrapolate beyond the range of data. So we don't have extreme observations. Then what we could do is to resort to some asymptotic distribution. But which distribution can we take? Because here it's easy to see that this distribution degenerates in the upper endpoint. Now, if you think in non-extreme topics, when you look for, when you study, for example, the sample mean, then there you meet degenerate distributions, because the strong log large numbers tells you that sample mean goes to a true value. And whenever you want to look at the rate which you tend to the true value, you have the central limit theorem, but the central limit theorem has rescaling sequences, so you rescale the sample mean in order to obtain something non-general. We do the same for the max, so we have to find normalizing sequences such that the maximum, this maximum here, tends to something non-degenerate. And if it does, then the asymptotic distribution has to be of this type here. This is called generalized extreme value distribution. It has three parameters, A, location, and the scale, but the most important one is this psi here, which is called shape, and basically determines the rate of tail decay. And the sign of psi tells you about the type of tail that you have. So you basically partition the set of distributions which have a limit, a GV limit, by means of the parameter psi. And you can have the fresh shape when psi is greater than 0, the variable less than 0, and the Bungle one for like tail distributions, for example, the normal and the exponential. In the bivariate case, or multivariate case, as I said, we look at dependence. And we can either study maximum, but the problem here is more difficult because the model is semi-parametric, in the sense that, well, first of all, you need to define a multivariate maximum, because in RD there is not a total ordering. So how do you define maxima? Well, take just component-wise maxima and do operations component-wise. And without loss of generality, consider the marginals of X and Y to be fresh shape. Because I say without loss of generality because it's enough to retransform back the margins for general cases. And again, if you're able to find, now you have sequences, normalizing sequences which are vectors now, but the meaning, the intuition is the same. If the scaled multivariate maximum converges to something, then this is the only possible limit, where now, of course, marginally you have the univariate GV, but this measure, nu, which is called exponent measure, has the role of describing the dependence between maxima of X and Y. And it is the non-parametric part of the model. As I said, you can also look not only at maximum, but exceedances over a high threshold. And there you want to look at the joint survival distribution. And there is this famous model by Ledford and Tony in '96, which describes basically the joint as n tends to infinity. Why is this model beautiful to me, but also to others, because this paper is pretty famous? It's because you have an index, eta, which describes the type of dependence that you have between maxima. So not a function anymore as before, but an index, which is more intuitive. And it is called extremal dependence coefficient. And given eta, this function L, I'm not going into the mathematical details of that, but given eta, it describes the strength of dependence that you have between extremes. And more importantly, these two quantities are connected to the upper tail dependence coefficient of the parent popula. Okay, so given the quick framework on extreme values, let's go to concomitance. So here you have again the sequence of ordered random variables. Now I've ordered them in a decreasing way. So here you have the maximum and the minimum. So what you do is to choose a number k fixed, and you use it to split the sample here in order to have a sample of size k and a sample of size n minus k. And what you are interested to look at, we are interested to look at, is the maximum, the joint of the maximum of this concomitance here and this concomitance here. That's because from this joint distribution, you can have information on how close this maximum is to the real maximum of the y variables. So our interest is in studying the asymptotic joint distribution of V1 and V2. Of course, we need to rescale them to avoid degeneracy. And in the seminal paper of Yoshi and Nagaraja, the literature on concomitance is not so recent, actually, and it's mostly concentrated in the late 90s, early 2000s. But now I believe it's the time to give it back and work on it. Anyway, they study already something like this. So the asymptotic distribution of the rescaled variables. Now pay attention, because this Cn and the n are the constants that you would use to compute the GeV limit of the variable y. But these a and tilde and b and tilde are different and are not absolutely related to those. And given this, and given that these constants are chosen in such a way to avoid some degeneracy, but again, in the paper, there is no explanation on how to find those constants. You have to try, basically, a lot of tentatives. And then they obtain asymptotic independence of V1 and V2. But we proved that Yoshi's result holds only when the parent copula is characterized by a lambda u, so upper tail dependence equal to 0. So you need to work with copulas exhibiting asymptotic independence. And this is not what we want, because we are interested in asymptotic dependence. So this is a huge restriction to us. And then we proved, okay, that some hypotheses of the theorem are redundant and can be conducted to lambda u. So we want to take advantage of the model that I mentioned by Ledford and Tom, describing the joint tail, to obtain something different. And this is our theorem. I will comment every single line of this slide. So this is the joint tail model extended in the bivariate case of Ledford and Tom. These coefficients alpha and beta are connected to what I called extremal dependence coefficients. So basically, they give us information on the type of dependence that you will have between the extremes of x and y. And then, provided that, and I will comment on this assumption later on, provided that this condition holds true where C is non-degenerate. No, produce music. Okay. Where the constants are now chosen like this. So in our theorem, we give the expressions of the constants, normalizing constants A and tilde and B and tilde, then you obtain this as limit for rescale V1 and V2. And you can observe that here you don't have asymptotic independence, because there is this x which links the two functions, whilst in the Yoshi's result, this H2 was independent of x and could be taken outside the integral. But this is something that you can see from our expression, because whenever lambda u upper tail dependence coefficient is 0, so this is 1, and here you obtain only the Frechet distribution. So when lambda u is 0, you go back to the case of Yoshi's theorem. So this extends actually the result in the case of copulas where asymptotic dependence is present. And now I want you to look at this type of conditional distribution, because after the example, I will comment on it, because there is still something to say. And I want to focus on that because it's the only part where the A and tilde and B and tilde play a role. quick example. Here you have a survival Clayton copula with Pareto margins. Then, after transforming to Frechet and working a bit on the joint survival, we are able to find this type of this expression for L and this choice of alpha and beta. So we basically apply directly our theorem in order to find H1 and H2. Of course, the integral cannot be done theoretically, it's difficult, but this is not a problem because it's enough to perform a numerical integration. And this is the result. The surface that you see is the surface coming from the application of our theorem, so the joint bivariate distribution of V1 and V2, whilst the black bullet points are the bivariate empirical CDF of V1 and V2, and you can see that they basically lie on the surface. And as diagnostics, this is the box plot of the errors in the sense the distance between each bullet point and its projection on the surface. So you can see that the error is pretty small, and also marginally, basically marginal distributions overlap. The empirical marginal distribution overlaps with the theoretical one, and also the error that you can make, even this peak, is pretty small. It's of the order of 1%, so totally acceptable. And now, let me comment a bit on the Gaussian case. Why the Gaussian? Because in Yoshi's paper, there is actually the Gaussian example, and they are able to find constants. But in our case, we proved that if you start from a Gaussian bivariate random vector, so with Gaussian margins, there is no hope to find constants A and tilde and B and tilde by taking left. And so what? This is connected. We found this beautiful paper by Effer and Resnick explaining that even if we are free to change the marginal of X as we want, we are not free to do that for Y. And I put this slide in the future because I still need to understand intuitively why this happens. Okay, I understand all the mathematical details of the paper, but actually not the intuitive meaning of that. So I'm open to any suggestion from the audience. And basically, yes, we are not able to find conditions on the general conditions on the constants in the Gaussian case. However, we solved it by using the result from Wellsworth and Tone, where basically they extend the joint tail model whenever the rate of relative to X and Y is different. So you are going to infinity with different rates, and the marginals are exponentials. Now, exponentials, the transformation in exponential is compatible with the Gaussian margins, whilst the Frechet wasn't compatible. Maybe because the Frechet is heavy-tailed and the Gaussian is light-tailed, but this is not enough to completely understand this. But anyway, by using Wellsworth approach and mixing what Yoshi did to find those constants, then we were able to find A and tilde and B and tilde whenever the margins are exponentials. And this L has the properties of the other L, that is bivariate, slowly varying, and technical details. And the final result that we have, this one, is basically coherent to what Yoshi found in their paper. Okay, so everything that I explained is available in our preprint, available online. And if you have any questions, or you want to contact me later on for explanations or comments, this is my email, and I give you some bibliography here.
Thank you very much, Amir. If somebody from attending remotely has some question or comments for Amir.
Yeah, Valeria.
Yeah.
Thank you, Amir Khorrami, for your presentation. I have only one question about the choice of K.
Yes.
Usually in the univariate case, there are some methods which is very known to choose K, but here, how to do?
Okay, so on K, we can comment in this way. So there is also another case which allows K to grow with N, actually at a slower rate with respect to N, but then this is called quantile case of joint maximum concomitance.
Okay.
The choice of the fixed K can be done by, maybe I can share again the screen. So basically here I said that the joint CDF of these two guys can be used to find, to have an idea of how much V1 is close or far to the real maximum of the Y variables, right? Okay. And basically you are studying the ratio between V1 and the maximum of the Y variables. And basically you can use K in order to, okay, you can put like an acceptable error that you can make by approximating Y maximum by V1, and then choose K by minimizing that error.
Thank you.
Any other question from people in the room, sitting in this room? Sophie, please.
Thank you so much for the presentation. I have exactly the same question as Ayub, but okay. If you say that K may be chosen to minimize the error, so do you minimize it in a theoretical point of view?
Yes.
Adding this constraint on the modelization?
Yes.
Okay, yeah. Meaning that in this case, so somehow K is going to be dependent on N, because if you compare with the estimator of the maximum that depend on your sample size, even if K is not a function of N.
I don't quite understand.
If you see that you can choose K to minimize the error.
Minimize in the sense that you choose some epsilon and delta, and then you ask whenever your F of the ratio in 1 minus epsilon is less than delta.
Theoretical F, not applicable.
The theoretical, yes.
The theoretical.
Okay, if not, let us thank again the speaker.